Okay, I'm going to explain about the up and with many too many. So in the previous example, we have 1 to 1, but how if we apply many to many? So the many to many means we have input and then we have output. And when we have another input, we will directly give the output. When we have an input, we will have directly output. So the structure will be similar with the 1 to 1 or the common RNN, but now it has an output. So when we finish calculating, for example, the H1, so after we have H1, we can produce an output. So I will give more description next week. So because it is related with the transformer with attention, so I think it's better to put all the details also in the next week slide. But for now, let's study more about the concept. So we have Y1 after we produce H1. We have Y2, the output after we produce H2. We have Y3 after we produce H3 and so on. As you know, we just use the same way. And for this output, we may have some kind of function. So sometimes we call it in this final layer or the output layer. In the output layer, we produce a value, and after we have the value, sometimes we need to produce a kind of function, a number function using logits. So we have L or logits 1, L2 logits 2, we have L3 logits 3, and so on. And we combine those into a logit factor. So we are going to discuss more about this one in detail for the transformer. So there are several structures actually when we deal with the neural network. If you look at the many to many, so many to many, we have an input and an output in the particular hidden state. And then next we have an input and an output in the particular hidden state. However, if we have many to 1, then we need to calculate the hidden state 1, the hidden state 2, we need to calculate the hidden state 3 until t, and we will produce an output. So after we finish all the calculation, the final h will determine the output. And we have the input x1, x2, x3. So every states or every step there is an input. So this kind of problem we can see in the sentiment analysis. So in the sentiment analysis, you may have word 1, word 2, word 3 until t. So if the word 1 is, for example, this, in our example before, we just use very simple factor. For example, this movie, maybe we have this movie is interesting. Then the easy factor is we have the x1 is 1, 0, 0, 0. We have x2 is 0, 1, 0, 0. We have x3 is 0, 0, 1, 0. And we have x4 is 0, 0, 0, 1. Yeah. This is the easiest way to factorize the word. But there will be different way to do this one. We call it embedding. Yeah. So the embedding, yeah, it can be different. You can use the 0, 1 axis or not. Or sometimes we can use frequency. Or sometimes we can use another representation, word embedding with encoding. So there will be some encoding function to do the word encoding. So I will explain more this one, not today, but today we are going to focus on the structure. So after we do the embedding, for example, 0, 1, 0, something like that, and we put it in the X, so we put this as the input to determine the H1. We put in the X2 and we use this one to determine H2. We have X3, we put into the function and we want to produce H3 and so on. And the classification means the result, the final result, because I know this word, this word, this word, and this word, then the final result I can classify whether this is positive or negative. So let's say I have another word or I have a testing word. This movie is good. So I can use this word, then I put it into the neural network, and at the end, I can classify whether it is positive or negative. Yeah, for your assignment, you don't need to use the neural network. Just use the common algorithm to classify the sentiment, whether it is positive or negative. So for many to one, there are some variants. So what is the variant? Can you see the difference? So this is many to many because we have, sorry, this is many to one because we have many input, but we have one output. The previous one is also many to one. So what is the difference? The difference is we will predict the output after we finish every step. After we finish every step, then at the end we want to predict whether it is positive or negative. In this structure, it is a little bit different, even though it is many to one, but after the step one, we want to do the prediction. So let's say I have the word this. Can I predict whether it is positive or negative? Of course, it is possible, but maybe the result is not good because we just have one word. So we can input another word. For example, is. After we put the is, we have another output. And again, we can check the output, whether it is positive or negative. Again, we will look at the loss function. So the loss function, we can calculate whether it is by scoring or only by the classification result. Again, with the next input, for example, this is good. Okay, because we have the word good, so we can have more confidence than that this sentence is positive. If we have more confidence about the result, then the probability will be high. If the probability is high, then loss may be small. If the loss is small, then we can say that, okay, the prediction is good. So this is another structure for many-to-one. For one-to-many. So the input is one, but the output is many. So when I do this input one time, it means I put all the information about the text at once, or I have a matrix and I have those matrix as the input in the step 0 or the step 1 to calculate the H1, and after that there will be no input. There will be no input. There will be no input. The input is only one time, and the other step will give you the output. So the input can be a matrix, and the result will be something like text generation. So yeah, we will learn more this one after we do the pre-trained model. So in the GPT base, so they use this kind of structure. You have one input or you have one question, but it can generate into several options. Or you can input into the several words. In some cases, one-to-many, it can be one input and then multiple output, and the input, it can be a kind of dummy input. So we call this is kind of dummy input. So the dummy input, we put we give the input in a particular form as a dummy variable in order to do the calculation in this step to produce the H2. We put a dummy variable to do the calculation in this step to produce the H3 and so on. So this dummy variable, there are several ways, there are several approaches. For example, we can put the dummy input as 0. Okay. So when we put 0, it means it will be added with 0. However, we need still to calculate the H1 with the particular weight plus the bias. In this case, even though it is 0, we still need to calculate with the weight plus bias. For this one as well, if we have the 0, so we need still to calculate the weight plus bias and so on. And in other case, we cannot provide the input in the step 1, step 2, step 3 until step n, but we can use the output. So the output from the previous states, the output from the step 1, it can be the input on the next stage. The output from this step, it can be the input to the next step. The output from this step, it can be the input to the next step. This is also another variant for one-to-many. And in the NLP, we will learn about sequence to sequence. So we have one sequence, and we want to combine with another sequence. So for example, we have many-to-one. So many-to-one, it means there will be many input and we want to produce a single output, and the single output, it will be used for the input on the next structure. So the one result or the one output, it will be for the one input, and we want to produce many output. So in this case, many to one. So we want to encode the input sequence in a single vector. So we want to encode this one into a single vector. And after we have the single vector, then we can make the one to many. So after we have all this one into one single vector, so we can have one weight, and then we use this property weight to produce the output, and so on. So we call this kind of structure is many to one plus one to many. And yeah, you will see there will be many variants about the sequence to sequence, or sec to sec. Now let's see an example if we want to apply this RNN in the character level language model. So we have the word hello. So you know the word hello, and yeah, we want to calculate the model. So we want to build a model so that it can predict what will be the next character. If I have the word HELL, I hope that the machine or the model can know that the next word is O. Then how can we do this one? Now let's suppose we have the vocabulary, which is the HELNO. So the vocabulary is the word that is unique. And I have the training sequence, which is hello. So HELLO. Let's just use the simple encoding. If it is H, then it is 1, 0, 0, 0, because we have 4. If we have E, then let's have 0, 1, 0, 0. If we have L, then we have 1, 0, 0, 1, 0. The other L, because we want to have a feature, and the feature should be unique. And the other L will be the same, 0, 0, 1, 0. For the O, we can have 0, 0, 0, 1. But in this training set, we want to consider only the 4 word, and we want to create a model whether the model later can predict what is the next character. So after we have this encoding, we can apply with formula that you learned previously. We can calculate the hidden layer. The hidden layer means the layer after you know the initial state or the H0 with particular weight and combine with the input. So in this case, after I apply this one, let's assume we have the hidden layer is 0.3 minus 0.1 and 0.9. And we have this one, 0.3, 0.1. We have this value. Okay. And after we have the hidden state for every step, Okay, let's say we have the output. We have the output layer. So the output refers to some value 1, 2.2 minus 3.0, 4.1, and so on. So usually this kind of output layer, you need to do more things, not only with this value, but we need to do something, for example, using the logics, or you need to do with some more function to make it as a probability. So you cannot just directly use this value to predict something. But let's suppose we have this output layer, and after we do something, after we do the logics or after we do some function, then we can determine the target character is E. But maybe based on this output layer, the the highest probability maybe is L, for example. Then there will be some loss, or there will be the misclassification. If there are some misclassification, the accuracy will decrease. If it is correct, then the accuracy is high. So we need to calculate for every of the output according to the output layer. Okay, this is just an example. Yeah. Let's say I'm using a softmax. So the softmax is the common function to convert this output layer into a probability value, or into a value that is normalized between 0 until 1. So if it is normalized between 0 until 1, it will be easier for us to uh, decide what is the result. Okay, based on this result, let's say the highest one is, okay, 0.84. And okay, the second factor represent the character E. Okay, the target is E. Then it is correct, or the classification is good. So we can do with other step. And before we do with the other step, because the task is to predict the next word or the character, the next character. So I can use this character, the one that I already know from this output. This will be the input for the next step. And the next step, because E is in the second index, then it will be 0, 1, 0, 0. So we can do again the same calculation. Okay. So we have the output layer, and using the softmax, okay, we have a higher value on the index 2, that is L. And after we have this one, you can do following the previous structure. So after we have H and the output is E, so E will be the input for the next step. So E as the input of the next step, we will enter the structure, and we have the output layer, we have the softmax, we have the result L. So L will be the next input for the next step. And we have this value. Okay, we have the possible word is L. And we go to the next stage. And after we go to the next stage, the result here is O. So using this structure, we have a confidence that after the word HELL, the most possible character is O. So we can do many things about this one. Maybe, yeah, you can do with the matrix multiplication. You can do with matrix multiplication with one hot factor. Just extract a column from the weight matrix. So we often put a separate embedding layers between input and hidden layer. So this kind of embedding layer. So this kind of embedding layer can be performed between the input and the hidden layer in order to calculate the hidden layer and in order to put a better value in the hidden layer. Okay. So a better value means something that might not be high or something that might not be very low. Because if the value is very low, let's say 0.00001, then there will be a problem. Or if the value is very high, in some cases, maybe the value not 1, but maybe 5, or maybe 10, or maybe 100, then yeah, it will be also a problem. So the value of this hidden layer, it cannot be very high and it cannot be very low. It should be in the particular range of values. That's why there are some methods that use some embedding function. And if you already learned in the neural network, we need to calculate the loss function. What is loss function? We call back propagation. The back propagation means after I have an input and it goes to the layer, let's say this is the hidden layer and this is the output layer. The output layer, this is the hidden layer, this is the input. And in order to update the weight, we can back propagate, and we can update the weight. But this states we are not going to update the weight because we are using the same weight for every of this hidden state. So what we need to measure is the loss. The loss here, the loss in this case, the output for every of the step, we will calculate with the actual value. So for example, we have the word hill and we want to predict the next O. So if the word X and we know the next word is E, okay, then the loss will be 0 because this word or this character is the same with this character, E and E, so the loss is 0. But let's say if we have the word hell in what we have in the model, it should be HELLO, but the model or the result give you L, HELLS. Then there is a loss, O and S, because it should be O, but the result is S. Then the loss can be measured, for example, 1. And so on. So we can calculate by the time, we can calculate all the output. So if we have until t, then we want to back propagate through the time. Through the time means we want to calculate the loss until we finish the iteration, until we finish the round. Forward through the entire sequence to compute the loss, and then backward through entire sequence to compute the gradient. The gradient, you know what is gradient? Gradient is the changes of the weight. So if there is a change on the weight after doing the backward or after doing the back propagation, so we call this is the gradient, or the easy word is the changes. If the changes is high or low, so that's something that we need to analyze. We can have another kind of back propagation through time. We call it truncated. So sometimes in the neural network, the run is very long. When the run is very long, of course, you may have some difficulties if your computer is not good. So some computers, if you use only the CPU, maybe it will run very long. If you have a good CPU, then maybe it will be a little bit faster. But if you have TPU or the newest one, they have the NU, neural processing unit. Yeah, of course, that one will be the best one. But our computer, maybe if it is CPU, then we need to find some strategy to calculate the result. So there are some strategy, we call it the truncated. The truncated means we run backward and forward through chunks of the sequence instead of the whole sequence. So we finish this chunk, or we truncate it. We call it, we cut. So we cut in some round, and then we continue to the multiple rounds ahead, and again we truncate it, or we cut into some multiple rounds ahead, and for every of the loss we will calculate it, and we want to get the average. So we call this is the truncated back propagation truth. Yeah, the RNN actually it is almost the same with the neural network. The issue is two. We can say the issue, the first big issue is the vanishing gradient. Or the second issue is the exploding gradient. Vanishing. Vanishing means it suddenly becomes very low or near zero, or it is zero. So the gradient problem, vanishing gradient problem, is one example of unstable behavior that you may encounter when training a deep neural network. So if the neural network has many hidden layers, then the gradients in the early layers will become very low as we multiply the derivatives of each layer. As a result, learning in the earlier layers become very slow. So if we have many layers like this one, if there are many layers, layer 1, layer 2, layer 3, 4, 5, 6, 7, 8, 9, and 11, and so on. So if more layers needed, of course, it will make the vanishing gradient problem, because the very low value, it will make the running time longer. And we have another issue, which is the exploding. So exploding is the opposite of vanishing. If we call the vanishing gradient, it means the value, it becomes nearby zero, or it can be zero. In exploding gradient problem, in some cases, the gradients keep on getting larger and larger as the backpropagation algorithm progress. So the value becomes high, 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 high in some of the steps. And if it is higher, higher until the end of the step, then it causes very large weight update and cause the gradient descent to diverge. So to diverge means it will be very big gap. And if it is very big gap, then you cannot get a good accuracy. You cannot get a good result. So this kind of problem, this kind of issue, usually we cover or we encounter it with the activation function. You need to select the good activation function, and most probably people use the sigmoid function. However, this is prone to the vanishing gradient problem. So this is the activation function. For every output, we want to smooth. Okay, we call it sometimes smoothing. So we want to put some activation value. So the value, it will be keeping between 0 until 1, but it will not be diminished into 0. And it will not be enlarged into 1, but it will be struggling in between 0 and 1. So there's another kind of function I mentioned to you in the previous one. It is the hyperbolic tangent or the tangent function. If the sigmoid value is in the range of 0 and 1, so the hyperbolic tangent, it will be from -1 to 1. And there is a common activation function, we call it REL, which is the rectified linear unit. It is from 0 until infinite. So until infinite means it can be very, very huge. But the huge value, it is, we can put some range. For example, I want to put the maximum value as 2. Then the maximum will be only until 2. So those three activation functions are the common activation function, but there are more activation functions that we can use. And in the Python library, in the TensorFlow, in the Keras, they have other activation functions that you can consider. So the activation function will help to make some of the weight into a good shape of the weight. So if you do not put any activation function, so you can see like this one. The value will be nearby 0 at some point in the positive, and the value also can be 0 at some point in the negative. So to avoid this one, so we put the activation function to make the value can be keeping in between 0 and 1. So the sigmoid function is one of the activation function, but the sigmoid function is still prone for vanishing gradient problem. Still prone means there is still opportunity, there is still possibility, there is still probability to be the vanishing gradient problem. But using the sigmoid function can be helpful. So the gradient can approach to 0 for large or small inputs. If the weights of the networks are constantly below 0, then the gradient will diminish slowly. So if it is below 0 or it is minus, then the gradients will diminish slowly. The gradient, as I mentioned to you, the changes between, for example, I want to know the weight between the step 2 and the step 1. Then the weight, if this one is very small or diminished slowly, usually it is like 0.001. This is already smaller, and you can get the weight becomes converged easily. So for the ReLU, is as the derivative of the ReLU function, it is either 0 or 1. 0 or 1. The error signals is also dependent on the width of the network. And if the widths of the network are constantly below 0, then the gradients will diminish slowly. So both sigmoid and ReLU will have the same idea. Okay. If you use the ReLU, yeah, there's a value, the value it can be 0 or 1. There is another kind of ReLU, which we call it leaky ReLU. When it is negative, it's diminished a little bit fast toward the negative value. And if it is positive, it goes highly on the positive side. So there are many other activation functions. It depends on the data, and of course, it depends on the characteristic of network. Some other variants, the RNN, we can look at the variants like GRU, LSTM. GRU refers to gated recurrent unit. LSTM is long short-term memory units, or LSTM. So both of those variants deal with the vanishing gradient problem encountered by a traditional RNN. And the LSTM is a generalization of GRU. So GRU is the more advanced of the RNN, but the LSTM is the generalization of the GRU. So if you look at the structure on the GRU, it is based on the gated. So there are some gate. So in the LSTM, there are some gate, and also there are some mechanism to do the forgetting and output. So that is the only difference. So the variants of the RNN, people say that the variant of the RNN are the difference on the gates. Gates is to remedy the vanishing gradient problem. So remedy means to fix the vanishing gradient problem. So we can use the activation function, but we can also use some of the variant of the RNN. Specific gates are used in some type of RNN and usually have well-defined purpose. So for example, the update gate. Update gate U, it has been used in the GRU in the LSTM. For the relevance gate R. So we can also look at the GRU and LSTM. But for the output and the forget gate, it is only in the LSTM. So if you look at this one, in the LSTM, it has more gate. In the GRU, they just use the update and the relevant gate. So in this update and the relevance gate, they just want to know what is the current weight that is good for the next step. The relevance gate, we want to know what are the most important value for the next step, and we can remove some unimportant weight. Okay, due to the time limitation, maybe I will explain this Google Colab on next Tuesday. Okay.